Good morning to all of you. I welcomes to all in our lecture series on solid state physics. In our last class we have been discussed about vibration of one-dimensional monoatomic lattice. In that discussion we have been discussed up to dispersion relations. To finding the dispersion relation we have been discussed. Rest of the things we have to discuss in our today class. Here in a short revision I am going to show you what we are done in our last class. This is a one-dimensional monoatomic lattice which is in the state of equilibrium. So if it will be start to vibrate, or if I am going to drag this monoatomic lattice towards this side, then this will be nothing but the so-called state of displacement. That means the nth atom which having the coordinate on the x-axis will be un. This is the nth atom having the coordinate is Na, because here we have been considered that between two atoms the interatomic spacing is A. Okay. So the nth atom having the x coordinate, here I have been written x coordinate will be Na, and n plus 1th atom the x coordinate will be n plus 1a, n plus 2a, like this. So when it will be displaced towards right, whatever it has been represented in this figure, this is the state of equilibrium. Okay, this is the state of displacement. So in this figure we can recognize one thing, that this nth atom is moved towards this much distance, that is represented by un. This is the displacement of nth atom towards this side. This is the displacement, that is un plus 1 is the displacement of n plus 1th atom. This is the displacement of n plus 2th atom, like that. Here we have been represented that the so-called un plus 2, un minus 1, un plus 1, un plus 2 are the displacements. Here I written, you can pause the video and you can write, but for this note you have to follow the last video. Okay. So these are the displacements of this corresponding atoms from their mean position. Okay. Here, as we have been considered that this is the spring, this model is a spring, that means each atom is attached with its neighbor atom. Suppose this is the atom, or we have to take, suppose this is the nth atom, and the nth atom is attached to n plus 1 and n minus 1 with a massless spring. And here we have been considered that each atom having the mass is m. Okay. As it is connected with a spring, or this model whatever we have been imagined for this vibration, it is a spring model, or we can say that it is a spring that it is connected with neighbor atoms. Okay, that all the things I have been written in detail in the note. You have to follow the note, but for this you have to follow the last video. In this case it is assumed that the spring are ideally elastic. Hence the force between any two atoms will be linear. That is, force required to produce an atomic displacement is proportional to the displacement itself. That means here you can consider the Hooke's law. Hooke's law means, as we are considered that this spring is a full elastic, that means how much I have to be pull this side. This atom, if it will pull this side, right side, the restoring force will be generated, that it will be tries to retain its mean position. It will tries to pull back. Likewise, when this atom will be displaced, a restoring force will be induced on this, when it will be pull this side. Okay, and this restoring force, what will be, it will be generated in this spring, that will be the directly proportional to the directly proportional to its displacement. Okay. So here we can consider a simple example that how the force is directly proportional to the displacement. See, suppose this is the nth atom will be attached with here. This is the spring. Suppose if I will drag this atom towards the towards the right somewhat, and I am going to leave, it will come back to its original position. I dragged somewhat distance towards the right, and if I will leave, then it will be returns to its original position, which is nothing but the so-called inducing of restoring force and the representation of the Hooke's law. Okay, now see, I dragged this much distance, and then I leaved. What is the force induced which tries to taken to its original position? If I will be increase the distance, then that force will be increased gradually. See, for this much distance, the restoring force is this one. If I will increase the distance, the restoring force will be more. If I will increase further distance, the restoring force will be more. That means if we have to increase the if we have to consider the increase of displacement, then the force will be also increased. That means here the force required to produce an atomic displacement is proportional to the displacement itself, or you can say the restoring force is proportional to the displacement in either in other way. Okay, only for that it is written that the restoring the force is proportional to the displacement. So let beta be the force constant of the spring and u be any arbitrary displacement. So hence the force exerted by the spring on the atom will be how much? It will be F proportional to u, that is displacement, or F equal to beta into u. This is equation number 1 we have been discussed. And then the net force. Now if we have to consider the nth atom is attached with it is attached with n plus 1 and n minus 1 and n plus 1th atom by 2 springs. So due to which the net force on the nth atom will be this much. And if we have to consider the Newton's second law, then it will be this much. This is equation number 3. In detail I have been discussed in the last video, you have to follow that one. Okay. Now if we have to solve the last equation, the solution of the equation number 3 will be in the form of this one. And for if this is un equal to u0 e to the I omega t minus k n a, here omega is the angular frequency and k is the wave vector. Okay, or wave number or propagation vector, we can say here it is propagation vector. Okay, so hence u n plus 1 will be this one, u n minus 1 will be this one. So by considering equation number 4 and 5, in equation number 3 we can obtain omega equal to this much. This is equation number 7 we have been given. And if we have to consider the equation number 7 in some other way, that is by considering us is by considering the see, if we have to consider that c and rho is the stiffness and mass per unit length, then the equation number 7 can be changed in the form of this one. Okay, so here Vs is the constant having the dimension of the velocity, and the equation number 7 and 8, the right hand side of the equation number 7 and 8 should have to be positive, because omega should be the positive always. So this omega will be 4 beta by m root over sine k by 2 modulus 2 by a Vs. Vs is the here the dimension of velocity, sine k by 2. This is equation number 9. So here we can found that this relation tells that relation between wave number and frequency. Hence it is called as the dispersion relation. Dispersion relation. So up to this much we have been discussed in our last class in detail. So you have to follow the last video up to this much. So today we have to start from here, that this is our dispersion relation we found. Okay. Now the omega versus k plot as shown in the figure, this one. Okay, you can see that the minimum value of sine will be 0. At k equal to 0, this will be 0. At k equal to pi by a, if I am going to put pi by a, the a got cancelled, it will be pi by 2, then it will be maximum. Sine k by 2 or sine pi by 2 will be 1, and the omega will be 4 beta by m. So this much value will be nothing but 4 beta by m root over this much value. Okay. Then why it is dotted line, that we are going to be discussed in our preceding sections. Okay. Now we are going to be derive, or we are going to be extract some important informations from that from this dispersion relation. So first we have to consider at the very low frequency. Okay. So from the equation number 9, we can perceive that omega will be less if k tends to 0. Here omega is nothing but 4 beta by m root over sine ka by 2. So if k tends to 0, then this value tends to 0 and k is going to be minimum. So here we have been written the same thing, that from equation number 9 we can perceive that omega will be less, very less, tends to 0 at if k tends to 0. That means sine k by 2 will be tends to k by 2, because we know that sine theta tends to 0 will be nothing but theta. Okay. So from equation number 9, for condition k tends to 0, this will be tends to ka by 2. Now the equation number 9 will be how much? Then the equation number 9 will be omega equal to 2 by a Vs into ka by 2, right? So I am considering this part. Okay, 2 by a Vs, here sin ka by 2 will be only ka by 2, so hence omega will be nothing but 2 by a Vs ka by 2. So a got cancelled, 2 got cancelled, this is Vs k. Okay, but Vp will be omega by k. Now we are going to consider the phase velocity and group velocity. As we know that whenever the more than one wave is going to be superimposed with each other, more than one waves having different wave length or frequency are going to be superimposed with each other, then there is two terms it will come out, that will be phase velocity and group velocity, and this will be looks like this one, like that, like a wave packet. So this will be a wave packet, and inside this the waves are moving with a mean velocity, that is called the phase velocity, but its center or highest peak will be moved with another velocity, that will be Vg. And we have been discussed in our previous video that for non-dispersive medium, this Vg equal to Vp, that means group velocity will be phase velocity for non-dispersive medium, that we are going to discuss here also. So yes, so here how we are going to be assume that many waves are going to be superimposed with each other. See, whenever this lattice is going to vibrate, then suppose this atom is going to vibrate with a frequency, and this atom will vibrate with another frequency, right? So if the two frequency vibration we are going to get, that means two simple harmonic motion we found with a different frequency. So if that two simple harmonic motions, and also you can consider this one will be the atom having the different frequency. So if we are going to consider these three atoms which having the different frequencies, so different simple harmonic motions, and they are going to be superimposed with each other, and the scenario will be phase velocity and group velocity that we can consider. And here we are considering that for low frequency Vp is nothing but omega by k. Okay, so in general we know that you can follow the previous video whenever I discussed phase velocity, group velocity. That video you can refer. I will give the link of the in my description. From that you can follow that one. That is there in detail we have been discussed that phase velocity is nothing but omega by k. Okay, is the phase velocity with which a single wave moves along a direction of propagation. That means the mean value, the average value of the velocity inside the packet. Okay, and the group velocity is nothing but d omega by dk is the group velocity with which a group of waves or its envelope moves. This represents the velocity with which the energy transmit along direction of propagation. So here it's in simple I can say that Vg is nothing but it is representing the motion of the particle. So this is the envelope, and at the center we can found the most probable position of the particle will be at the center. So this envelope moving with a velocity, or this peak where the particle will be there, the particle peak is moving with a velocity. That velocity will be nothing but called as the group velocity. So here this group velocity represents the velocity of the particle. So here the velocity of the particle, that means the mass is transported from one place to another, or we can say the energy is transported from one place to another. So like that it is written over here that velocity with which energy transmitted along the direction of propagation. So if this wave packet is moving this one, energy also moving in this way with the velocity having the group velocity. Okay. So from equation number 10, this is equation number 10. From equation number 10, one can found that omega by k equal to Vs. Omega by k equal to Vs and d omega by dk also Vs. So we have to refer the equation number 10. Now the equation number 10 we can found omega by k equal to Vs and d omega by dk also Vs. So here omega by k Vs represent the phase velocity, d omega by dk will be equal to Vs also represents the group velocity at low frequency. So at low frequency what we found? We found the phase velocity is the same as the group velocity. Phase velocity is same as the group velocity. So whenever we found the phase velocity equal to group velocity, this will be called as the non-dispersive medium that we are going to be discussed with. So in this case large number of atoms, all type of displacement undergoes all type of displacements at a homogeneous string as shown in the figure. So this will be the dynamics of the atoms for the low frequency. Okay. Here we can say that all the atoms are in phase. Means they are moving with a phase. That means I can show you that this vibration mostly they are moving, all are moving one direction or all are moving this direction. If for low frequency all the atoms either moving right or either moving left, like that at low frequency. But at high frequency all the atoms are moving in different directions. This atom is moving this direction, maybe this atom is moving this direction at a particular time. So for at low temperature or low frequency at a particular time all the atoms either moving right or either moving left, or we can say are in phase. So if it is so, then that motion, that this uniform or homogeneous motion can be represented by a wave like this, having the wavelength is lambda. Okay, that means in a string, suppose we are going to consider a string, in a string in which way the wave will be transmit, if we are going to put a force at the end of the string, then that type of wave can be imagined at the low frequency. Suppose this is a string. If I am going to be give a force at this point, then a wave will be propagated like this. See, this is the yes, you can imagine that on this line each and every atom will be a linear one dimensional lattice you can imagine on this line. So this is atom, this is another atom here, like that. So if at a instant at a particular instant at the low, for the low frequency, either all atom is moving this side or moving that side. So that can be represented by a wave like this, or it is representation of a string. Means if, suppose if it is a string, I am going to put a force over here, a wave is propagating like this. Wave is propagating like this. That means all the atoms are in phase. Here this is moving up, means along with the nearby atom is trying to move up like this. It is the wave is look like a wave which is in the string. Okay, in a homogeneous string, that type of wave it can be produced, will be produced inside the crystal at low frequency. So this is the representation. The motion approaches that a homogeneous line that I have been explained. In this case, Vg, Vp equal to Vs equal to omega by k, that is omega is proportional to k. That means here Vs is constant. So omega will be equal to Vs into k, or omega is proportional to k. And the dotted curve, the dotted line, the dotted curve in the figure 1 is the dispersion relation for this case. So for this case, the dispersion relation between omega and k will be a linear. That means if k will be increased, omega will be increased. That means I can say up to this much portion, k increases, omega increases. So here you can see at a certain value of k, or after certain value of k, the non-linearity starts. That means omega not proportional to k. After this k value, omega not proportional to k. Means up to this much linearity of omega and k we have been found. That means up to this frequency, suppose up to this frequency, we can found Vp equal to Vg equal to Vs. Okay. Next we have to consider at higher frequency what will be the behavior. At higher frequency. So at higher frequencies, the phase and group velocities are different and are obtained by the equation number 9. So here from the equation number 9 we know that from the equation number 9 we can found Vp, which is nothing but omega by k, will be 2 Vs by k into sin ka by 2, right? And Vg is nothing but d omega by dk, because for lower frequency we have been considered that sin ka by 2 is tends to ka by 2, but higher frequency we have to consider sin ka by 2. Okay, so here sin ka by 2 will be as such we are going to be considered, because with variation of k the omega will be vary sinusoidally. So only for that here Vp will be omega by k will be this much. Let this is equation number 11, and Vg will be equal to d omega by dk will be this much, 2 by a into a by 2. Now if I am going to differentiate this one with respect to k, it will be this much, or Vg will be, we found out that d omega by dk will be equal to Vs into cos ka by 2. Let this is equation number 12. Okay. So from equation number 11 and 12, this equation number 11 and 12 tells many physical things that we are going to discuss here. Watch carefully. Okay. from equation number 11 and 12, it can be found that Vp and Vg are different and depends on frequency. Vp and Vg both are different. Okay, this is referred to as phenomenon of dispersion, and the medium is called as the dispersive medium. Here I can give you one example before we have to proceed further. See, suppose this is a prism, right? When the white light is incident on this prism, then different colors is going to be dispersed. Dispersed means spreaded out, different colors. So in this way, red, yellow like this, violet like this. So different colors is going to be separated out from the white light when it is passed through a dispersive medium. Because when it is passed through the dispersive medium, each color will be behaves, or each color will be have their own refractive index, hence they have own different frequencies. Okay, so here I am going to see. Here I am going to give an example. See, suppose this is a prism. Okay, when the white light is going to be passed through the prism, then the white light is going to be separated out with different colors, red, yellow, violet like this. This is nothing but called as the dispersion. Here white light have one particular velocity, right? Or we can say one particular refractive index. When it is passed through a dispersive medium, or this is the material of glass, prism is the material of the glass. So when the white light is passed through this dispersive medium, the colors which is integrated inside the white light, it is separated out, because inside the dispersive medium, the different velocities or different frequencies of the different colors are going to be move with different speed. Okay, here I can show that this is suppose the wave packet photon. Okay, this is the photon, and inside this all the colors are there. When it will be interact with a dispersive medium, then different colors, suppose red, yellow, green, violet, they will be move here. Without dispersion medium, they will move with the same velocity. That means inside this velocity, the so-called phase velocity will be equal to the photon velocity. Group velocity will be equal to the group velocity. Phase velocity will be equal to group velocity. But when it will pass through a medium, dispersive medium, the group velocity will be not equal to phase velocity. That means all the velocities, all the frequencies, all the different frequencies, or all the colors, or we can say different frequencies of the light which is inside the white light, they will be moved with different velocities. The red light will be moved with different velocity, yellow light will be different, green light will be different when it will pass through the a dispersive medium. Then it will be spreaded out, and we are going to say that this is the so-called dispersion. Okay, so here the same thing it has been observed. The same phenomena we can accept here also, that this is referred to as phenomenon of dispersion. What I told that here Vp and Vg are different depending upon the frequency. See here Vp is different with Vg when it is passed through the dispersion. So the same phenomena we can accept over here, that this is referred to as phenomenon of dispersion, and the medium is called as the dispersive medium. So when the frequency will be higher, then the medium will be called as the dispersive medium. Okay. A similar phenomenon of dispersion can be considered that when white light passed through a medium, or here medium is the means prism, whose refractive index is a function of the frequency. Then when what I discussed over here, that when the white light passed through a dispersive medium, then each color have the refractive index will be different and they will be separated out. Okay. So here we found that for longer wavelength, Vp equal to Vg equal to Vs, that is dispersion effect is negligible. Longer wavelength means, in our previous discussion, in this discussion we found that Vp Vg equal to Vs, that means dispersion will be not there, but negligible, and the medium behaves like a homogeneous continuum medium. But in this case, at higher frequency, we can found the different frequency of waves moving with different velocities, or the medium will be looks like say dispersive medium. That means I can say that here all the atoms, whatever we have been considered that one dimensional lattice, here all the atoms are moving with different orientation. Suppose this is moving this direction, at a particular instant this is moving this direction with different frequencies. So if it is so, then we are going to get many numbers of waves with different frequencies, and the so called medium will be called as dispersive medium. Okay. Now at frequency we have to consider 4 beta by m root over. So this will be the highest frequency, because from equation number 9 we can found that this way, from equation number 9 we can refer the equation number 9. See, equation number 9 is 4 beta by m root over sin ka by 2. So here omega will be maximum means this much, because sin ka by 2 or sin theta having the maximum value will be 1. So the maximum value of the frequency will be 4 beta by m root over. Now we are going to consider the frequency, or at the topmost frequency or the highest frequency. So at frequency omega 4 beta by m, what will be the behavior inside the lattice, that we are going to discuss in third eye section. Okay. Now from equation number 9 we found that we found omega equal to 4 beta by m root over, which is maximum angular frequency of the vibration, as sin ka by 2 modulus will be 1, that is sin theta maximum value will be 1. That implies this can be possible, omega will be this much if sin ka by 2 will be equal to 1. That means when k equal to pi by a, or 2 pi by lambda, k is nothing but 2 pi by lambda will be pi by a, or lambda equal to 2a. So at the maximum frequency in which the lattice is going to be vibrate, due to which what type of wave we are going to be found out, that wavelength will be 2a. So here this is the figure I can show you. This is the vibration of the maximum frequency with which the wavelength, here the wavelength is 2a. Okay. So from here one atom to another atom, this distance is a, this distance is a, and so here one atom to one atom, or trough to trough distance is 2a, or you can say that from this to this is a, this to this is a, so this wavelength will be 2a. So, and from equation number 11, 12, by considering k equal to pi by a, we can found Vp will be equal to, from equation number 11, this equation number 11 which represents the phase velocity. Here if we are going to consider the k is equal to pi by a, k is equal to pi by a, then what we are going to get, this is pi by a, this is the pi by 2. Okay, Vp we are going to get 2 Vs by pi. Let this is equation number 14. And Vg how much we are going to get? Vg will be nothing but that will be Vs cos k by 2. Vg is how much? Vs cos k a by 2. Here k we are going to be put as how much? Pi by a. If we are going to put here k equal to pi by a, then Vg equal to 0. So from equation number 14 and 15 we can perceived one thing that these two equations indicates that there is no transform of signal or energy, because Vg is 0. Vg is 0 means there is no transform of energy. That means we can say that these are the atoms. The conjugative atoms are moving opposite direction. This moving this direction, this moving this direction. This moving this direction means this moving this direction. In this way we can found a standing wave. Okay. We know that for the standing wave there is no transform of signal or energy. So hence this standing wave can be represented by this figure is here. The standing wave formation at omega for the frequency omega equal to 4 beta by m. Okay, where lambda equal to 2a, lambda equal to 2a. So here I told that this to this distance is a and this to this distance is a. So this will be the so called wavelength. I suggest that you have to pause the video and you have to write the note, because notes are useful at the time of exam. So from the above description it is found that only the vibrations of the frequency, see at this frequency there is no transport of energy. This frequency tells us about the standing wave, but only the frequency which is less than that of this 4 beta by m root over, or that is 2 Vs by m, can propagate through the lattice. Hence the lattice behaves as a low pass filter. Okay, low pass filter, because the lattice allows the frequency less than this frequency, which transmit only if the frequency lies in between 0 to one particular value of the frequency. Here I have one simple example for you, that if we are going to consider a typical lattice structure crystal having the lattice constant approximately 1 angstrom, then it will be 10 to the minus 10 meter, and the velocity, if it will be considered 10 to the 4 meter per second, then the maximum frequency will be observed in that lattice or crystal, which can be transmitted is maximum frequency will be 10 to the power 1/4 second inverse. From this equation it can be found. So approximately this much we can found. See, this is will be what Vs by a. Vs is 10 to the 4 by a is 10 to the 10, so 2 will be there. You can say that 2 into 10 to the 14 or approximately 10 to the 14 hertz or second inverse frequency will be possible for the lattice. Having the lattice constant will be this much. Okay, now we have to move at any frequency. What exactly happening inside the, or what are the things we can observe at any frequency, that is omega 0 less than that of the 4 beta by m root over. Okay, now consider the vibrational motion of the lattice corresponding to any frequency which is less than that of the 4 beta by m root over, which lies in the vibrational range, and we defined in just before that vibrational range in the lattice will be from 0 to this much, from 0 to this much. So vibrational range, if a frequency, if we are going to consider which is lies in the vibrational range, a plot of dispersion relation in the equation number 9, the dispersion relation equation number 9, for k values, for values of k lying beyond plus or minus pi by a is shown in the figure 4. So this is the dispersion, relations graph, whatever we have in the first figure. First figure we have just this much up to pi by a to minus pi by a to pi by a, up to this much we have in the first figure 1. So I have been extended over this much and this side. So this figure 4 is nothing but is the extension of can be visible, no? Okay, it is the extension of figure 1. Figure 1, where is figure 1? I can show you. This is the dispersion figure. This is here, this is in between minus pi to pi, but I have been extended over plus pi by a to beyond that one, minus pi by 2 beyond that one. Now here, before we have to be proceed, I am going to be recall one thing. See, whenever we have been discussed Brillouin zone, you can remember this is your Brillouin zone, right? We have been discussed, that is in between. See, this is the first Brillouin zone. This is the first Brillouin zone. So this is the line what we have been drawn, having the equation is pi by a. That means here this point is pi by a, this point is pi by a, this point is pi by a, this point is also pi by a. Okay, because from here to here this is nothing but 2 pi by a. This is the distance 2 pi by a, this is the distance 2 pi by a, and this is nothing but our k space. K space here, this is kx, this is ky. If it is k space, then it is called as what? Which space? Reciprocal space. May you have been remember, I have been given the note itself. You can see that a crystal lattice is a lattice in the real space or in coordinate space. However, reciprocal lattice is a lattice in the reciprocal space or k space. So we can represent a real space lattice in the reciprocal space lattice that we have been studied in our last classes, and the reciprocal lattice space is nothing but the so called k space. So here it is represented in the form of k, here kx, ky. That means this is the reciprocal space. Reciprocal space means from here, from any point to this point, another point, is the distance is 2 pi by a. See, this distance is 2 pi by a, this distance is 2 pi by a. So if we have to consider, suppose g vector, lattice vector, then I can consider along x-axis. I am telling n 2 pi by a. If n is a integer, if I am going to multiply 2, 3, then from here, if I will be multiply with a integer 2, 3, 1, 2, 3, 4, 5 like this, and this will be transformed on here. This is the lattice point. So 1 2 pi by a, another point, 2 2 pi by a, another lattice point, 3 2 pi by a, this is another lattice point. So one dimensionally the reciprocal lattice translational vector can be represented by n 2 pi by a, means each and every lattice points are repeated with the distance of 2 pi by a in the reciprocal space, where this same lattice repeated in the real space having the distance is a. That means if this lattice is going to be represented in the real space, then the spacing between the two atoms, two nearby atoms, will be a. So here from one atom to another atom it will be a. Here I written a. Okay, but a star mod will be 2 pi by a. Here is a. If we are going to move if this is a square lattice, then from here to here it will be a, but b star modulus will be 2 pi by a. That means a lattice, a square lattice, if it is repeated with A, again A, but if it is transformed to K space, then it will be repeated to 2 pi by A, again this is 2 pi by A, this is another 3 pi by A, like this. 2 pi by A, 2 pi by A, 1 2 pi by A, 2 2 pi by A, sorry 2 2 pi by A, 3 2 pi by A, like this. So it will be repeated with over and over with integral multiple of 2 pi by A. Okay. So here you can see this is your first Brillouin zone. First Brillouin zone length. See how we drawn the first Brillouin zone. Then we have to take the middle position of the interatomic distance. Then we have draw a line, and in detail I have been discussed. So this is the first Brillouin zone. The first Brillouin zone length from here to here, this will be nothing but how much? Kx is equal to pi by A. See, this line equation is minus pi by A. Okay. So this is the this is nothing but minus pi by A. This is nothing but pi by A. Pi by A. So this distance is nothing but 2 pi by A. Distance 2 pi by A. So first Brillouin zone is minus pi by A to pi by A. Then 2 pi by A to 2 pi by A. Here minus pi by A to minus 2 pi by A. Minus 2 pi by A will be called as the second Brillouin zone. The second Brillouin zone exists in between minus pi by A to minus 2 pi by A, plus pi by A to plus 2 pi by A. One dimensional, you can consider itself two dimension. So and the repetition of the atoms in the reciprocal lattice will be integral multiple of 2 pi by A. That also you can found whenever we have been discussed in the reciprocal lattice to simple cubic lattice. At that time you can found that A star reciprocal lattice vector is nothing but 2 pi by A of along x axis. Along x axis it will 2 pi by A. So the lattice vector along y axis is nothing but 2 pi by A j cap. Z axis 2 pi by A k cap. So again I am going to be say to you one thing, that if a lattice is represented so this whatever we have been taken in our case, this is the lattice, it is repeated over and over in the real space having the distance is A, again A, it is repeated with A and A. If it will represent in the K space, then it will be repeated with 2 pi by A. Suppose we have to take this is 0 origin, this atom is origin, then this will be 2 pi by A, this much distance will be 2 pi by A, then again this will be 2 into 2 pi by A, this will be 3 into 2 pi by A. That means interplanar spacing in the reciprocal space or in the K space will be 2 pi by A, but in the real space it will be A. Okay. Now we have to proceed further whatever we have been represented in the figure. Okay. So this is the figure 4 is represent the dispersion relation for a range of k values along with Brillouin zone. A number of k values correspond to the same frequency omega 0. That means what I am going to be explained with. So this figure is nothing but the dispersion relation, but it is extend over the k values. K value is extends towards infinite along towards infinite this side. See here, this is 0, this is minus pi by A, this is pi by A, and we discussed just now that minus pi by 2 A to pi by A is nothing but belongs to first Brillouin zone. Okay, first Brillouin zone. Then pi by A to 2 pi by A, here minus pi by A to minus 2 pi by A, the region, this region and this region is nothing but belongs to second Brillouin zone. Here this and this to this is second Brillouin zone. then 2 pi by a to 3 pi by a, this region, and minus 2 pi by a to minus 3 pi by a, this region and this region is nothing but belongs to third Brillouin zone that we have been studied in our previous classes, and here only I represented in one dimensional. There we have been represented, there that picture, this one is the representation of the Brillouin zone in 2 dimensions of simple cubic lattice. Okay, here the representation of one dimensional simple cubic lattice, one dimensional, in which the periodic lattice are in between 1a to a. This is one lattice. Next another lattice we are going to found, the distance is a, another lattice the distance is a. So with repetition of lattice with a distance of a, and if I am going to be transform this to the reciprocal lattice, then this lattice will be repeated with the distance of 2 pi by a. So if this will be the 0, this location in the reciprocal lattice will be 2 pi by a. This will be 2 into 2 pi by a, like this. That means in between two lattice the distance will be 2 pi by a in the k space or in the so called reciprocal space. So this is the representation of different Brillouin zones. Now in the Brillouin zone, one interesting things you can observe here. See, from 0 to pi. Now before that I am going to be say that this is the so called highest frequency. This is the highest frequency point, that is nothing but 4 beta by m. But here we are going to consider a frequency which is less than that of the higher frequency. That means any arbitrary frequency we have been considered, that is omega 0. This is the omega 0. Omega 0. And if I am going to be consider a line which is parallel to the x axis, then it will be intersect here. That means you can see that in the different k values having the same frequency omega 0. This is the omega 0. Okay, so here you can see k1 at k1 the frequency is omega 0. At k1 or for k2 this is also omega 0, the same frequency. K3 also omega 0, here also minus k1 omega 0, minus k2. So different wave numbers having the same frequency. This is the another information we can found from the figure. That means whenever we have to consider the frequency which will be less than the frequency, the highest frequency, then that frequency will be belongs to the different k values. That means maybe this one in the first Brillouin zone, this is k1, this is in the second Brillouin zone, that is k2, third Brillouin zone k3. k1, k2, k3 are different, but represents or in this k values we can found the same frequency. So here the same thing it has been written from the figure 4. This is from figure 4. It can be noticed that a number of k values, that is k1, k2, k3 etc. are associated with the same frequency omega 0. That means lattice can propagate a number of wavelengths, lattice corresponding to these k values at the same frequency omega 0. So what is the meaning of that? Lattice can propagate a number of wavelengths. Okay, because if k value is going to be changed, that corresponding wavelength is going to be changed. How it will be? Because we know that k is nothing but 2 pi by lambda. This is the corresponding wave number or propagation vector, also called as propagation vector, and it is mathematically represented by 2 pi by lambda. So k changes, lambda changes, because 2 pi is constant. So at the different k values, obviously we are going to get the different wavelengths. That means at k1 the frequency is omega 0. That means the vibration having k1 but frequency is omega 0. Try to listen carefully. having one displacement or one vibration or one dynamics for k1 having the frequency omega 0, or we can say that for a dynamics having k1 means corresponding lambda 1 frequency, because k1 is nothing but how much, 2 pi by lambda. So for lambda 1 the frequency is omega 0, for lambda 2 frequency is same omega 0, for lambda 3 frequency is same omega 0. That means we can found in the lattice, whenever the one dimensional lattice is moving in this fashion, in one dimensional fashion, in that case we can found at a particular frequency many waves are propagating with different wavelengths. So how it will be possible? This will be possible by represented this figure. See, this is one wave, this is another wave, okay, but in this wave, see, in this is the wave having the wavelength is lambda 2, okay, this is the wave having the wavelength is lambda 1, okay. So here suppose that initially this is the two atoms, it is attached here, and all the atoms will be periodically present over here, here and here along the line. And the one dimensional lattice means here one dimensional lattice will be initially at this position, or you can say the static position. When it starts vibrates, either this one, along this way, along one dimensional, it has to vibrate, because we are taken the one dimensional lattice. So it will be, when it will starts to vibrate, one atom can be vibrate with same frequency. This atom can be vibrate same frequency, this atom vibrate can be same frequency, but same wavelength, different wavelength. See what I am going to be say that if we have to consider this wave, okay, this is the wave having a smaller wavelength as compared with the lambda 1, but the displacement, this atom is displaced from here to, from the initial position to here. This is belongs to this wave, and this is belongs to also this wave. This is displaced to this, from this to this. That means this is belongs to this wave, and this displacement is belongs to this wave also. So all the displacements, whatever represented in this figure, this is belongs to both smaller wavelength and larger wavelength. Okay, here I am going to say one thing, that this is the representation only, but the vibration is along this way only, but this is the representation. So that means this atom is displaced this direction, but it is represented in transverse wave. It is represented for our understanding purposes, that this atom is displaced some distance along x-axis, but represented in transverse way. Okay, here what we discussed from the dispersion relation, that different k value may be different k value or corresponding different wavelength, but they have also same frequency, means different wavelength having the same frequency vibration we can found in the lattice, when the frequency will be less than that of the maximum frequency. So same thing it has been written. Yes, here I don't have the space in my note, only for that the name of the figure I have been written over here, but you have to draw the figure, this one, carefully, beautifully here, and write the name of this figure at the bottom of this figure. Okay, so here corresponding the k values at the same frequency omega 0. Physically it is shown in the figure, this one. This is the physical representation of the different wavelength having same frequency omega 0. Okay, where the same set of atomic displacement represent two waves of different k value or wavelength here, because k is to wavelength, so wavelength having the same frequency omega 0. I have been explained here that this atom is displaced, this displacement will be belongs to this wave and also belongs to this wave. So one displacement is belongs to both the waves. So different wavelength may be, but frequency will be same. Now another some beautiful things that I have to explain here, you just watch. Okay, it can be noticed that another things we can notice from the figure 4 what it is. See, I am going to show you. See, first Brillouin zone is belongs to from this point to this point. Okay, minus pi by a to plus pi by a is nothing but is your first Brillouin zone. Okay, see, the first half of the first Brillouin zone, that means 0 to pi by a, is the behavior is this one. In your dispersion relation is this one, the behavior is this one. Okay, so from minus pi to pi, this is nothing but this portion is nothing but first Brillouin zone, and the first half, if I am going to consider that it is the behavior is this one. Now I am going to consider the second some other Brillouin zone where this type of behavior we are going to be found. See, this behavior is found at here in your third Brillouin zone, right? In your third Brillouin zone. That means I can say the right side of third Brillouin zone, this is the right side of the third Brillouin zone, this is the left side of the third Brillouin zone, right? Right side of the third Brillouin zone is equivalent behavior to the right side of the first Brillouin zone. Carefully you have to watch and you have to listen also. Right side of the third Brillouin zone is equivalent behavior to the right side of the first Brillouin zone. Now this is the behavior. This behavior is belongs to what? This behavior is belongs to second Brillouin zone, but right side. So right side of the second Brillouin zone behavior of the right side of the second Brillouin zone. This is from minus pi by a to 2 pi by a is nothing but second Brillouin zone. So in the second Brillouin zone, the behavior of the graph is similar with left side of the first Brillouin zone. See, this like this one, from if you have considered 0, from 0 to like this. So this type of behavior is equivalent to left side of the first Brillouin zone. Okay, likewise, if you are going to take the higher Brillouin zones and their behaviors, they will be matched with either this half of right half of the first Brillouin zone or left half of the first Brillouin zone. Are you got my point? Here different Brillouin zones except first Brillouin zone, they are going to be matched with either right side of the first Brillouin zone or left side of the first Brillouin zone. Here third Brillouin zone behavior is matched with right side of the first Brillouin zone, and right side of second Brillouin zone is matched with left side of the first Brillouin zone. So whatever the Brillouin zone we are going to be consider up to infinite, and this side also infinite, all the Brillouin zones dynamics can be reduced to first Brillouin zone. That means second Brillouin zone dynamics can be represented by the first Brillouin zone equation. That means if we have the dynamics of the atoms in the first Brillouin zone, that will be have some equation. That equation also can be useful to represent the second Brillouin zone dynamics, because here you can see the right side of the second Brillouin zone behavior is equivalent to left side of the first Brillouin zone. That means simple I can say that any Brillouin zone and its dynamics can be represented or can be reduced to first Brillouin zone. Same thing whatever I discussed I have been written, I am just reading, you just watch. Okay, from figure 4 that backside it is there. You draw, I only suggest that up to this much you have to draw this figure, and whenever you have to watch this explanation, you have to put your figure with your right side. Okay, so here from figure 4 it can be noticed that right half of the second Brillouin zone is similar to the left half of the first Brillouin zone. We have been saw there. Okay, similarly we found the regions of third and higher Brillouin zone matches with either right or left of the first Brillouin zone with difference in k values. Okay, see, suppose we are going to consider third Brillouin zone. This third Brillouin zone is matched with right side of the first Brillouin zone, but if we have to consider the frequency corresponding to omega 0 and its corresponding k value is k3, but here omega 0 corresponding k value is k1. Now that means if we have to consider from 0 to pi, the k values are different. If we have to consider the k values from 2 pi by a to 3 pi by a, so here only k values are different, but behavior is same. Okay, same thing it has been written over here. Hence, so must match with either right or left of the first Brillouin zone with a difference in k values. Okay, so hence any arrangement of atomic position and its vibration representing a sinusoidal wave of wavelength lying in the higher zone, what I discussed, higher zone, can be represented or reduced to corresponding to a sinusoidal wave for which k or lambda lies in the first zone or first Brillouin zone. So what it is tell to us that these lines are told that any dynamics we are representing in which way? In the way of the transverse or sinusoidal wave, any dynamics. Suppose a dynamics in the second Brillouin zone. Second Brillouin zone, so that dynamics can be represented with the solution. Solution means this is the dynamics, means the displacement, right? So that displacement can be represented by in this way, in this format. Okay, suppose that dynamics in the second or third or higher zone, which can be represented or reduced to corresponding to sinusoidal wave equation for which k or lambda lies in the first zone. Okay, so that dynamics can be reduced to first Brillouin zone. How it will be, I am going to be explained here. That means if we are going to take the higher zones dynamics, then it will be similar to the first Brillouin zone. How it will be, that I have the verification, you just wait. Therefore, it is not desirable to consider the vibration contained in the regions other than the first Brillouin zone. So except other than the first Brillouin zone, other zones dynamics should not be, it is not desirable that we have to be considered. It can, because it can be transformed to first Brillouin zone. Okay, so only for that it is not desirable. A k value corresponding to second or higher zone can be made to transformed to first Brillouin zone by subtracting a suitable integral n multiplying of 2 pi by n. So this lines meaning that I am going to explain with a example. You just wait. That means any k value corresponding the higher Brillouin zone can be transformed to the first Brillouin zone by subtracting a suitable integral multiple of 2 pi by n. That means k will be subtracted. If n 2 pi by a, then it will be reduced to first Brillouin zone. How it is, I am going to show you. Wait. This happens because we know that any system crystal which is periodic with period k in the real space is also periodic in k space or in reciprocal space with the period 2 pi by, what I discussed many times in this video. You just recall it. That means translational vector in the real space, suppose we are going to consider one dimensional, then it will be na. Translational vector will be na, but translational vector in reciprocal space will be n into 2 pi by a. That means in the real space, the atoms will be situated or the atoms will be at along x-axis. Suppose we are going to consider along x-axis. Along x-axis means the atoms will be at 0, a, 2a, 3a like this along negative x-axis, minus a, minus 2a like this. And Gn means in the reciprocal lattice it will be 0, 2 pi by a, 2 into 2 pi by a, 3 into 2 pi by a, 4 into 2 pi by a, like that. Here this side it will be, that means it is repeatedly we are going to found the lattice point in the reciprocal lattice with the distance 2 pi by a. Okay, that I have been also discussed. Now I am going to show you one thing. You just observe it. Okay, you just observe, try to observe how the higher zone's behavior or k value can be transformed to the fast Brillouin zone. You just see wait 1 second. See the fast Brillouin zone length is how much? The fast Brillouin zone, in manually I am going to be show you. So one thing you can observe here, that see fast Brillouin zone, that means minus pi by a to pi by a. Minus pi by a to pi by a is 6 centimeter. I have been taken in the 6 centimeter. Okay, that means from 0 to pi by a is 3 centimeter. So if I am going to be add both the side of the second Brillouin zone, also we are going to get the 6 centimeter. So this is the second Brillouin zone, 3 centimeter. This side also 3 centimeter, second Brillouin zone. Now I have a dynamics which is at higher zone, and it has to be transformed to the fast Brillouin zone. See here, this is the dynamics which is inside the third Brillouin zone. Which one? This one is the third Brillouin zone. But this behavior is where it is at right side of the fast Brillouin zone. Okay, so this k value or and on the k value or the here the dynamic in the fast third Brillouin zone, here k3 have frequency omega 0, k1 is omega 0. This k3 is going to be transformed to the fast Brillouin zone. How? In which equation? You just watch. See here, k3 is here. We know that one Brillouin zone, the fast Brillouin zone having the length is how much? 6 centimeter. We calculated by the scale. Now if I am going to subtract some 2 pi by a, because it is periodic, some 2 pi by a, I am going to be reach with the same behavior with the fast Brillouin zone. How? See from here see this behavior is like this. I am going to subtract 6 centimeter. See 6 centimeter if I have subtracted from here, exactly I reached at where? K1. Exactly I reached at K1. So how much I have to subtract from here to here? I have to subtract K3 minus 2 pi by a, right? K3 minus 2 pi by a. Then it is transformed. This K3 is transformed to fast Brillouin zone. So I am going to take another example, K4. Okay, I don't have space, so I adjusted in this way. So this is the another portion of this curve, that this is 3 pi by a and this will be the 4 pi by a. Okay, and this will be the K4, approximately here will be the K4. Okay, here K3, here K4. So K4 is in the fourth Brillouin zone, and that fourth Brillouin zone dynamics will be transformed to the fast Brillouin zone. See, this will be the behavior of the left hand side of the fast Brillouin zone. You got my point? This behavior is like this. So this behavior is matched with the left hand side of the first Brillouin zone. That means this K4 is transformed to minus K1 by subtracting of n 2 pi by a. So here from K3 to K1 I subtracted 2 pi by a. So K4 to K1 I has to subtract either 2 into 2 pi by a, 3 into 2 pi by a, like this, means with a appropriate integer with 2 pi by a I have to subtract from this K4, then I will get that K value which will be inside the first Brillouin zone. Is it so or not, that you have to check. Wait, see. So here we are at K4 approximately. You just watch here you are at K4. Okay, K4 means here the subtraction is, if I will subtract from first 2 pi by a, first 2 pi by a means how much? 2 pi by a means 6 centimeter. If I will subtract from K4 2 pi by a, I will be reach at K2. Okay, see, 6 centimeter approximately K2. Approximately K2. If I will be reach. This will be like this one. Okay. Now if I will subtract, then where I have to reach? I reached that where? K2. From K4, when I subtract 2 pi by a, if I will subtract 1 2 pi by a, then I will be at K2. Okay, but K2 is the second Brillouin zone. We not required. Then I have to subtract next 6. Next 6 means I reached at minus K1, which is belongs to first Brillouin zone, and exactly same with the dynamics of this one. So here how much I have been subtracted? I have been subtracted from K4 minus 2 into 2 pi by a. I subtracted this much from the K4 and I reached inside the first Brillouin zone, which is same dynamics with the dynamics of in the fourth Brillouin zone. This is the dynamics of fourth Brillouin zone. I reduced to first Brillouin zone by subtracting from K4 with a required value, that is integral multiple of 2 pi by a, whatever I written over here. Okay, suitable integral n multiple of 2 pi by a. Okay, so here I can show you that the K4 in general we can write K4 minus n 2 pi by a will be reduced to, here K4 2 into 2 pi by a will reduce to first Brillouin zone. Suppose first Brillouin zone K value is considered as suppose K is belongs to first Brillouin zone, not K1. Here I represented K1. Let K1 is represented as K. This can be found, or the K4 is going to be transformed from here fourth Brillouin zone to first Brillouin zone by minus 2 into 2 pi by a. Or in general I can write K first Brillouin zone will be K dash means is belongs to K dash is belongs to K of any Brillouin zone, is transformed to first Brillouin zone by subtracting of n into 2 pi by a. So in general I can write this one. Okay. So is it so? It is correct or not? For that verification I have been represented here the mathematics. You just follow up. Okay, so this can be verified, whatever I have been written over here. See, whatever I discussed about these things, not to be right in the note. You just watch this video and try to be clear whatever I written, how it is transformed like this. But these things whatever written in your note, that is here subtracting suitable integral. Why it is subtracting, I explained. So this, after subtracting, is we are going to get the same answer or not, that for the verification, this is the things. This can be verified by considering displacement of nth atom. Let nth atom having displacement in any arbitrary Brillouin zone. We don't know where it has to be displaced. In any arbitrary Brillouin zone, that can be represented by un is equal to u0 e to the power I omega t minus k dash. K dash is belongs to that Brillouin zone, that arbitrary Brillouin zone, k dash into Na. Now this can be transformed to fast Brillouin zone by considering k equal to k dash minus n 2 pi by a, whatever I discussed. Okay, so that implies k dash will be equal to k plus n 2 pi by a. So here I am going to substitute this one here. Okay, so it will be un equal to u0 e to the I omega t minus k plus n 2 pi by a into Na. Okay, is equal to u0 into e to the power u0 e to the power I omega t minus k into Na into e to the power I, here I n square, a got cancel 2 pi. Okay, so here u0 e to the I omega t minus k Na, k here k is belongs to fast Brillouin zone. Okay, so into e to the power minus I, here I written that n1 is nothing but n square. See, n is the integer and n square also will be the integer, positive integer. So n square will be the positive integer that is represented by n1. n1 is also a integer, here I written. Okay, so un equal to u0 e to the I omega t minus k Na into this value will be always 1. This value will be always 1. Because you can see that e to the power minus I n1 2 pi. Okay, this will be nothing but cos n1 2 pi plus minus I sin n1 2 pi. We know that sin any 2 pi, this is integer, this is not fraction, this is positive integer, because n1 is nothing but n square. So this will be the 0 value and this will be always equal to how much? 1. So hence this is written as 1. Okay, so will be equal to u1 equal to u0 e to the I omega t minus k Na. So this solution you can found that this solution which is matched with equation number 4, whatever the representation of the of the each atom is displaced in the fast Brillouin zone. This is the equation number 4, is representation or displacement of the nth atom in the fast Brillouin zone. Okay, so if we are going to consider any atom in any Brillouin zone can be transformed by considering k dash minus n 2 pi by a, n 2 pi by n in the reciprocal space. So here k is nothing but k dash, this is k is belongs to fast Brillouin zone, it will be k dash any belongs to any Brillouin zone, k dash is the belongs to any Brillouin zone minus n 2 pi by a. If we have to substitute this value, or k dash will be substitute with this general equation, it is transformed to the equation belongs to the displacement in the fast Brillouin zone. Okay, so un equal to u0 plus u0 into I to the power into u0 into e to the power I omega t minus k Na, which is solution is the matched with equation number 4. Hence, for simplicity, the dynamics in any Brillouin zone can be transformed to fast Brillouin zone. So for simplicity, so we should not be bothered about other Brillouin zones and dynamics. Only just simply we have to transform that dynamics to the fast Brillouin zone. And here we have been verified that one. Okay, so here also we found that the new k dash given identical result with different wavelength. Here k dash, here we have been applied k dash na, so k dash means different wavelength. So different wavelength having have different maybe different wavelength have same frequency, what it is representing in this figure. Okay, so this is the all about discussion of one dimensional lattice, monoatomic lattice vibration. We have been discussed. You go through these two videos, write down the note properly and prepare for your exam. I am not going to suggest that this all the notes are useful for your exam. For exam you have to reduce the note by reducing the equations, by reducing these write-ups. So the most important things for the exams are you have to represent the 4 points at higher frequencies, at this frequency, at any frequency, what type of behavior that you have to show, and the graphs whatever we have been discussed, that are the most important, that you have to be put inside your exam whenever you are going to be write this question in your exam. Okay, this may be the maximum 8 to 10 mark question. So you just you have to, this is, I think in my case it is 11 pages. Okay, this is 11 pages note, you can say. Do not be fear about that. You can reduce these things up to 4 pages. It can be, no problem. These derivations can be reduced. Okay, and this writing also can be squeezed. This derivation can be reduced also. You just reduce the note, and these discussions no need to write in your exam. You just go through this for your understanding. I suggest go through the video at least 2 times, this video 2 times, and write your note properly. And if you got any doubt, you can contact with me. So thank you so much for watching this video. Thank you.